Okay, so we learned yesterday up to this. Okay, so ni number of cells, ni number of particles when you have to distribute them in gi number of cells. Okay, then how many ways can be there? There may be ni plus gi minus 1 factorial number of ways, and total number of ways of realizing this distribution is something like this. So gi multiplied by ni plus gi minus 1 factorial. So these are some statistical mathematical rules. So you have to, I urge you to remember them. So from physics point of view, it is difficult to explain, but they come from statistical mechanical point of view. And whole of this derivation, the derivation means what we want to get. We want to get this particular equation, the derivation of Bose Einstein distribution law. So how this number of particles, ni number of particles, okay, what is the ni number of particles, how it can be expressed? It can be expressed in terms of this gi number of cells, and then this e to the power alpha, e to the power ui over kt minus 1 in this expression. So this is something called, written here, Bose-Einstein distribution law. So this particular topic is all about arriving, all about getting the derivation of this law. Okay, and this is very, very statistical or mathematical, whatever you can call. So this probability, okay, the number of different arrangements or meaningful microstates in the ith compartment, okay, it is written J, I don't know, it should have been ith compartments having ni indistinguishable particles is like the number of different arrangement, it is like this, okay, wi equal to gi ni plus gi minus 1 factorial divided by ni factorial and gi factorial, okay. So this expression you have to remember. Okay, so in if you are like asked to like derive this distribution law, so you don't have to write all these things in the middle. Okay, it may become very complex. So you can show up to this. Okay, up to this you can show, and then this w, the number of different arrangements, you can show this directly. Okay, from there. So from here, we have some like mathematical steps. So this gi factorial, it can be written as gi multiplied by gi minus 1 factorial. Okay. So, okay, so I think you know already this. So this type of relationship in permutations. Okay, so gi factorial. Okay, gi factorial. I mean, here you have to substitute that expression. Okay, if you have substitute that expression here, so here it will be gi divided by, for this one, gi get cancelled. So ni plus gi minus 1 factorial, and it will be ni factorial gi minus 1 factorial. Okay, so just substitute it here, and you will get this probability, number of different arrangements, this probability as an expression something like this. So this equation 1 gives us the number of different arrangements of distributing ni distinguishable particles among gi cells in the ith compartment. Okay, ni number of particles, how you can distribute in gi cells in the ith compartment. So similar expressions will be obtained for other compartments. Okay, so for other compartments also, like ith compartment, or maybe first compartment, second, third, fourth. So similar expression one can also find for other compartments. So this is for the ith compartment. Okay, how ni number of particles can be distributed in gi number of cells in the ith compartment. So as per that, for other compartments also similar kinds of experiments can be found out. Therefore, the total number of different arrangements for all n particles. Okay, for all n number of particles, how many total number of different arrangements will be there? Okay, so it is just, you have to multiply all these arrangements. Okay, all these distributions. So this is for the ith distribution. Okay, so that is what we have just found out in equation 1. Then what will be the for the first compartment? First compartment expression is something like this. Okay, n1 plus g1 minus 1. So n1 factorial this. This is the second one, n2 plus g2 minus 1. Okay, something like this. This is the ith compartment, which has also already been found out in equation 1. And this is the kth compartment. Okay, and k plus gk minus 1 and something like this. Okay. So and this thermodynamic probability, okay, this expression, so this W expression is something called thermodynamic probability. And in order to calculate this thermodynamic probability, you have to multiply the probability for each cell. You have to multiply the distribution of each cell, each compartment, first compartment, second compartment, third compartment, up to the ith compartment, and then up to the kth compartment. Okay. Then how you can write them simply in summation. So this I equal to 1 up to I equal to k, and then ni plus gi minus 1 factorial divided by ni factorial gi minus 1 factorial. Okay. So here in the previous case for the ith compartment, it was simply this expression, but here when you have to find this thermodynamic probability, so you are considering all the different compartments, and in that case, this particular sign is coming, okay, because you are considering all the available compartments in the system, okay, in the Bose Einstein gas or boson gas, whatever you call it, in the system, and that's why this particular expression is coming. So again, for examination purpose or to make things simpler, after this expression you have found out the probability distribution for the ith compartment. So for all the compartments, the thermodynamic probability, for thermodynamic probability, you can directly write this expression. This one equal to this W in bracket N1, N2, Ni up to Nk. You can write that it is equal to this particular expression. Okay, so you can directly write it. Okay, then most probable macro state. Okay, so okay, so most probable macro state. So some expression for that you have to calculate. So so macro state means like it's a property which like many different microstates like combine to give one macrostate. Okay, so maybe macrostate and microstate definition you will learn during the introduction of this course, introduction of this statistical mechanics course. So it is statistical mechanics or physics. So what is this course exactly? So I always get confused. So in one class, it is statistical mechanics. It is statistical mechanics or physics. Okay, I forgot it. So in MSc also this course is there. So I think I forgot anyway. And microstate means like it is kind of like each parameters you have to know, or the quantities which describe the motion, okay, the motion of individual particles. Okay, so that is kind of microstate. So each parameter that you have to learn. And macrostate, macrostate means when you combine all these microstates. Microstates are again those parameters which give us the motion of the particles. And macrostate means so they give us information about all the microstates together. Okay, that is something called a macrostate. Okay, so most probable macrostate, that is what we have to consider, and there are some mathematical derivations, etc. Let us see. The most probable macrostate corresponds to the state of maximum thermodynamic probability. Okay, maximum thermodynamic probability means this W value has to be maximum. Okay, this W value has to be maximum. That gives us the most probable macrostate. Okay, So in equation 2, both Ni and Gi are very large numbers, so that neglecting one, okay? Okay, so in equation 2, if we consider that this Ni, the number of particles in the ith compartment, and Gi, this the number of cells, if they are very large quantities means if they are much larger than 1, then how we can write the expression for this thermodynamic probability W? So the expression for thermodynamic probability W can be written like this. So Ni plus Gi factorial, okay, one would be one we may eliminate because one is just a number now. It does not make much sense because both Ni and Gi are very large quantities. And in the denominator part, Gi minus 1, in this case also we can eliminate minus 1 because again, Gi is a very large quantity and we don't have to consider this. Okay. So, okay, so what we have to find out, we have to maximum thermodynamic probability, okay, maximum probability we have to find out. And in order to find that out, there are some mathematical steps here. So what we have to do is, so here you see it's like a division term, right? So it's this quantity divided by this quantity. So in order to do this division, make this division term a simple one or simplify this type of division. So what we'll do, we'll take the natural logarithm, a natural logarithm of this equation. This equation, I think you may give some number, maybe if yes, as per your convenience, maybe equation 3 or something like that. So if you take natural logarithm, then you see, so this ln w, so natural logarithm. And we are not writing this n1, n2 up to nk type of things. Okay, equal to I equal to 1 to k, this summation term will be there. So the natural logarithm of this expression minus, okay, natural logarithm of this ni factorial and minus natural logarithm of gi factorial, okay. So this is just happens when you take logarithm, and I think yeah, you are familiar with this relationships of logarithm. Okay, so these are like easy things. Okay, so now this when there are this factorial quantities, so this factorial quantities we get, then there is in mathematics or this type of subjects, there is something called a Starlings approximation. Okay, so what is this Starlings approximation to make such factorial expressions easier to deal with is something like this. So logarithm of this n factorial is equal to n log n minus n. I repeat, logarithm of this n factorial is equal to n log n minus n. That means in this particular equation, again, if as per your convenience, you can give this equation some number, because you have to use in that equation this particular Starling's approximation. Okay. So logarithm of W is equal to I equal to 1 to I equal to K. Then this quantity, how, so this is factorial, okay, factorial. This quantity, how you can write as per Starling's approximation. So if you break it, so n log n means it will be ni plus gi, and log n means log of this quantity, log of ni plus gi. Okay, and minus n means here ni plus gi. Okay, I hope you have understood this part, which can be derived from this part. Okay, so is it fine? I hope you understood this. Then this natural logarithm of ni factorial. So ni factorial is directly follow from here. So here it is minus symbol. So it will be minus ni log ni, and this minus minus will be plus. So it will be plus ni. Okay. Now this natural logarithm of gi factorial. So natural logarithm of gi factorial, again you break it as per Starling's approximation. So what we'll get is gi this log of gi okay, gi natural logarithm of this n sorry natural logarithm of gi plus gi. Okay, plus means this is a minus symbol here, so minus minus will become a plus. Okay, minus gi natural logarithm of gi plus gi. Okay, so this is like something like we get and what next okay, you see here if you do this simplification further, so this ni is minus and this ni is plus, so they get cancelled. So this gi will be minus if you break it, so this gi and this gi will get cancelled. Okay, so we will be having this quantity and this quantity and this quantity. Okay, these three expressions will be left for us because all other ni gi so they will just get cancelled because of plus minus signs. Okay, so let us check next what we can have. Okay, so maximum thermodynamic probability is what we have to find out. Okay, to get the state of maximum thermodynamic probability, we have to differentiate the expression for this logarithm of W and make it equal to 0. You see, because this is if some function has a maximum value, then you already know that the differentiation of that particular function has a value which is equal to 0. Okay, so we have to differentiate this equation. Okay, of course by cancelling this ni and gi. So whatever terms are left, that particular equation you have to differentiate and then make it equal to 0. So upon differentiation, so what are we supposed to get? So this differentiation of natural logarithm of w, it will be okay. So this one and this one first, and then ni will be there, dni. Okay, and then ni plus gi, and then you differentiate this particular term. It will be 1 over ni plus gi. Okay, here 1 over ni plus gi, and then it will be dni. Okay, it will be dni, and gi is assumed to be a constant. It is a constant quantity, so the differentiation of dgi is equal to simply equal to 0. Okay, so have I written somewhere that dgi is equal to 0? No. Anyway, so dgi equal to 0. So and then which quantity we have to differentiate? This quantity. Then this quantity we have to differentiate. So it will be a ni. Okay, log of ni it will be dni. Then minus ni 1 over something like this. So ni, so the differentiation of this ni, log of ni will be 1 over ni, and then this ni it will be dni. Okay, so what will we have? What we have? Okay, so after that, so these terms, you see, this term gets cancelled. This term gets cancelled. Okay, so dni will have, so here also dni will have, because this ni gets cancelled. So so we will have the dni and dni. So these two terms are just get cancelled. Okay, they will cancel each other, they will become 0. So we'll be left with only this term and this first term. Okay, so this differentiation you check yourself. Okay, so I hope you know how to differentiate these logarithmic quantities that you check. That's easy to follow. And gi is taken to be constant, assumed to be constant. So gi has not been differentiated. Okay, so this logarithm of I mean the differentiation of this logarithm w will give us I equal to 1 to I equal to k, and then dni this term will have minus this term will have. Okay, all other terms after differentiation they get cancelled. Okay, how we can rewrite this equation, this particular equation? So this d logarithm of w is equal to, okay, see, we have two logarithmic terms. One is this one and the other one is this one, okay? Logarithm of ni plus gi and logarithm of ni, okay? And this dni is found to be a term which is present on both sides, okay? So something like this we can write. So logarithm of ni plus gi over ni, and dni is a common term, so equal to 0. Okay, so equal to 0, and this maximum thermodynamic probability. Since we are here to calculate the maximum thermodynamic probability, and therefore when we know that when a given function has a maximum value, its differentiation has to be equal to 0. Therefore, we have made d ln w equal to 0. Okay, so we have got this equation. So you can give it some number as per your convenience. So we have given some number 3, equation 3 here. So, but apart from this, we have to consider two more things. So, conservation of the number of particles. Okay, total number of particles. So ni is equal to constant. Okay, if ni is also a constant quantity, because it represents total number of particles, because we know that the number of particles cannot change. Okay, so what we'll have, so dni, if it is a constant, so dni will be equal to 0. Okay, and conservation of total energy of the system. Okay, if total energy of the system we consider, suppose the system has a kind of constant energy. Okay, in that case, what you'll have, u equal to constant, total energy is constant. Therefore, d capital U is also equal to 0. But if there are ni, so for all the particles, so suppose n1, n2, n3, all the particles, suppose how we have written this expression, let me write it. Suppose n1 number of particles have u1 energy. So n2 number of particles, suppose they have u2 energy. Okay. So in that case, for all the particles, how we can write? So summation over u1 dni equal to 0. Okay. So as per this equation, so we can write something like this. Okay. Okay. So next. Okay, here I have done a simple mistake. The mistake is that here it should be, okay, so let me check, let us check first what is done in equation 6, and then I will point out. So multiply equation 4. Equation 4 means this one. Okay, equation 4, here it is written in Roman, here it is written in English. So multiplying equation 4 by alpha and equation 5 by something called beta. So what we get, alpha dni, okay, alpha dni. So multiplying, I mean, over all the particles, so over all the particles which are present in the system. So what we get, so alpha summation of I equal to 1 to k dni plus beta I equal to 1 to k. So it should have been ui, but I have, by mistake, I have written it to be ni. So remember that this is not ni, this should have been ui. Okay, so you note it down, you point it up, and you make a point of this. So it should be ui dni. Okay, because here it is ui dni, not ni. Okay, beta yeah, and summation by I to k. So for all the particles, so we are directly doing this. Okay, alpha dni summation number I equal to 1 to this k and beta. So alpha and beta are constants. Okay, alpha and beta and some constants. So beta I equal to 1, summation over I equal to k, and this uy dna equal to 0. Okay. So now from equations 3 and equation 6. Okay, equation 3. So in equation 3, this quantity is equal to 0. And in equation 6 also, okay, maybe I can zoom out a bit. Equation 3 and equation 6. And equation 3, this quantity is equal to 0. And equation 6, this quantity is also equal to 0. That means since therefore this quantity and this quantity can be made equal. Why? Because both are equal to 0. This is maximum thermodynamic probability, and this is just from energy and number of particles. So this one, this equation from conservation of number of particles and from conservation of energy principles. Okay. So both these terms are, both these left hand sides are equal to 0. So this quantity may be made equal to this quantity. That is what is written equations 3 and 6. So this quantity was dni and equal to this quantity. Okay. So I hope you have understood this how they are made equal. So now arrange this equation, arrange this resultant equation. You see dni is common in all the expressions. Okay, dni is common in all the expressions. So bring these other two expressions also to the left hand side, and you see what we get. The summation over I equal to 1 to k, and this logarithm of ni plus gi over ni minus dni is taken common because it appears in each quantity. So alpha minus beta ui. Okay, minus alpha minus beta ui equal to 0. Okay. So you have understood this. Okay. So now, as the various DNIs are independent of one another, the above sum is equal to 0 if the expression within the bracket vanishes separately for each value of I. Okay. So various DNIs are are independent of one another. So it is like so this term has been made equal to 0. Okay. So if from this equation, and if this term is made equal to 0, how we can write it? We can write this logarithm of ni plus gi over ni equal to alpha plus beta ui. Okay. Okay, so beta is a quantity which is generally defined as 1 over kt. Okay, so 1 over kt means 1 over Boltzmann constant multiplied by the temperature in the absolute scale. Okay, so that you have to remember beta ui or ui over kt, since beta is this term. Okay, kt. So, so this quantity ni plus gi over ni, it will be e to the power. Okay, so natural logarithm, you know, this is term will be written as e to the power alpha and e to the power ui over kt. Okay, we can write like this. So, oh, sorry. So from this expression, okay. So I hope you have understood this. So it was just exponential term. Okay, so in logarithm. Okay, so from here, what we have to find out? We have to find out the value of ni. Okay, so ni value is what we need to find out. So 1 plus gi over ni equal to e to the power alpha e to the power ui over kt. So ni is an expression which is ni equal to gi over e to the power alpha and then e to the power ui over kt minus 1. Okay. So, so far whatever we have done, so many steps. So all these things have been done only to find out this particular equation, which is given equation number 7. So this is the Bose Einstein distribution law. That means this ni number of particles, how they will be distributed in gi number of cells. Okay. So that is what we have to find out. And the distribution will depend on like the energy, temperature, and the Boltzmann constant, etc. These things. Okay. So EY is stands for energy. Energy, what type of energy it is? It is the kinetic energy. And K is Boltzmann constant. T is temperature. So this is the equation. So this relation gives the most probable distribution of particle for a system obeying Bose Einstein statistics, and give most okay, the most probable distribution of particles for a system obeying Bose Einstein statistics, and this expression is also known as the Bose Einstein distribution law. Okay. So this is what is directly given in your syllabus, and that is how you can find out the Bose Einstein distribution law. Okay. So you have to remember this expression. Okay. Because this expression will also be useful in other uh, uh, in some other topics, like and in the next topic we are going to learn about Bose-Einstein condensation. In Bose-Einstein condensation, we also have to refer this particular relation a few times. Okay. Yeah, you have to a few times you have to refer to this particular relation. So okay, so of course this is a separate topic in itself. How would you derive this Bose-Einstein distribution law? And from here on, other topics will also follow. Okay, like Bose-Einstein distribution. So I hope you have been able to catch most of the things of this derivation. So you have to start with some basic things like an independent identical particles. Okay. So identical means that's why they are indistinguishable. Okay. So that is where physics ends actually. So if you may be wondering, so what is the physics in here? You have done so much of mathematical derivation. So where is the physics? The physics is initially these assumptions, identical particles. Okay. So any number of particles can be in any number of compartments or cells as per Bose-Einstein statistics. And finally, whatever this you are finding out, whatever this number of particles. So number of particles in a given cell. So that also depends on some energy values and so on. But rest of the things in the middle of the things, you have to find, you need to take help from statistics. You have to take help of statistical mechanical stuff. Okay, something like this. Okay, so yeah, so you have to make it simpler in your own terms. How you can make it simpler. So although a lot of things have been written here, so this is the expression that you have to directly write, or this expression, equation 1 will also do. Okay. So from here on, you have to like then from equation 1, this equation 2, and then most probable you have to differentiate. You have to take natural logarithm, differentiate, make equal to 0, and this number of particle conservation and this energy conservation things, and some more simpler mathematical steps for logarithm and exponentials, and you finally get this particular expression. Okay, so this note is already available in Google Classroom, and in the next class, today we don't have much time, 5 minutes, and in the next class we are going to...
Then Google Classroom, we did not get the joining code.
Oh, you don't have the joining code? Oh,
No, sir.
so you should have told me. No? So why you did not tell me? Okay, so I am just a minute. Now itself, I am. So is the WhatsApp group open now? No, okay. I am doing it from my mobile. Okay. Oh no, joining code is there. 3 students have joined already. So 3 students have joined. Isaac, Kunal, and Pankaj have joined already.
I did not get that message, sir.
Oh, but I think I have already shared it in. Okay, I'm sharing it again. Okay, I have given it in your WhatsApp group. Okay, so I think that's all for today. So you also study, go through the notes. It's a bit mathematical. And the next topic will be Bose Einstein condensation. And after we learn Bose Einstein condensation, we'll learn about some thermodynamics of Bose Einstein degenerate gas. Okay, so those two topics are also important. And okay, I think that's all for today. And someone please take the screenshot. Only 2 people are present, and then we can end today's class.
Yes, sir.